if we want to more generally describe the value of an annuity after some number of years, we do have these, well, not particularly nice formulas here that I'm going to describe in a second, but before I get to that, I'd like to give a bit of the mathematical context for where they come from. Because it's one thing to memorize, or at the very least have written down these messes, but I think it helps you remember how exactly they come together if you've actually seen how they come together. So from our last example, we can say that generally describing the value of an annuity is something like a sum of terms where you have P plus P times 1 plus R, that is the evaluation from the principal times the interest for that year, along with P times 1 plus R squared from the year before and the third year back, and so on until we get all the way to the very beginning where we have P times 1 plus R raised to the power T minus 1. Because we have all of those powers of the interest value there, 1 plus R, where you start essentially at a 0 and go all the way up to the last one at n minus 1. A lot like what we did when we were talking about number conversions back in chapter 4, where this construction is a bit of a thing called a geometric sum. It's not quite a geometric series. It's a bit indeterminate, but it doesn't go on forever. That's something that was hidden inside of the end when we were looking at things from chapter 5 that we didn't quite get into that got left as extra credit. But if you want to see that, you can. For our purposes, though, you can just get this idea, at the very least the most important thing we have here, by just thinking a little bit carefully, thinking a little bit subtly. Where if we look at what we have up there, that whole mess should be equal to A. And I'm going to do something that is, like I said, very subtle. So I'm going to take all that thing, say it's equal to A, and then I'm going to multiply both sides by 1 minus R. Excuse me, 1 plus R. 1 minus R would do something else. Not very helpful, maybe. Where when we multiply A times 1 minus R, we have A times 1 minus R. Super. But on the other side, on the right side, all those things with P's, we're going to get a P attached to a 1 plus R. Then in the second term, the 1 plus R that was there before is going to get squared. The third one we get cubed, fourth, fifth, and so on. I'm going to skip some of these terms in here just because I don't have a ton of space and go all the way down to the last one, where that term at the very end, that P times 1 plus R raised to the power T minus 1, is now going to become a P times 1 plus R raised to the power T. It's been made whole, as it were. And great, we have a whole bunch of terms. Super useful. But actually what we can do here is notice that if we take something like that and subtract it from something like this, well, on the left side we got something very manageable. A times 1 plus R minus A. Meanwhile, on the right, we're going to have two very big messes. But when we write out a couple of the terms from those messes, we'll have a P times a 1 plus R. And then I'm going to skip all the stuff in the middle because, like I said, I'm pretty short on space. To P times 1 plus R raised to the power T. And then we're going to be subtracting from that P, a P times 1 plus R, and a whole bunch of other things up to a P times 1 plus R raised to the power T minus 1. Where, yeah, like I said, it's a real mess, and I've tracked into a side that I don't like to be in. But what we should see here is, looking at all of these terms, a whole lot of this stuff is going to go away, because we've got a 1 plus R with a P right there, a 1 plus R with a P right there. There's going to be a 1 plus R, T minus 1, and a P hidden in there, and everything else in the middle is also going to be hidden else in the middle there. So, for one, this is going to get caught over there. We know this is going to get caught in here somewhere, and all the other stuff in there is going to get stuck too. So all we're going to be left with, actually, is just the value P times 1 plus R raised to the T minus P. Now on the other side here, we can factor in that A. We'll have an A plus AR, subtract an A. All you're left with is AR, and then we pretty much have our formula here, because I'll factor out a P. We'll get P times 1 plus R raised to the power T minus 1. And then I'm going to divide over an R, and we get our formula. A is equal to the principal times the quantity, 1 plus r raised to the t minus 1, all over r. Where it's very, very important that you include those brackets when you're dealing with it, because even though it's subtracting 1, and you think yourself subtracting 1 doesn't make that big of a difference, remember, we're not just subtracting 1, we're subtracting an entire principal. That's not huge, but it is relevant, and you can have a big difference there, especially as you're talking about larger and larger time periods. And if we extend this, because this only tells us about something like our last example, something like a annually compounding interest with one value into the annuity every year, if we instead talk about it compounding n times per year where we invest once per compounding period, so if we do it monthly with the investments, we'd have monthly interest, we can very easily extend this to write it as A, our value is P times the quantity 1 plus R over N raised to the NT minus 1 all over R over N, which actually works for basically the same reason as this, except you've got a bunch of N's and the whole thing looks a little bit messier, but it ends up going to almost exactly the same place for almost exactly the same reasons. So now that we have our general formula and a sense for why our general formula works, let's take another example. For this example, we have that to save for retirement, you begin depositing $750 into an IRA at the end of every month for the next 40 years. Yeah, you probably don't have $750 to put there now, but let's pretend, like the book usually does, we're pretending things are good. If you will get a 6% interest that compounds monthly, what will the value of the account be after 40 years, and how much of that value will come from interest? So here, we could go through the steps of adding all of those 40 times 12 terms, but no, I don't want you to do 480 computations manually. I'm not that mean. Well, you might disagree, but don't tell me that. Point is, we're going to use the general formula here, where in this case, we have that P, our investment, is $750 every time. R, in this case, the rate is 6%, and the number of periods here is 12 because it compounds monthly, and T, almost forgot the most important part really, is here 40 years. Or if you want to talk about this in terms of the number of times that it'll compound, like I said, 480, which should give you an idea of the fact that this is not going to be a small number. But to be sure, we can plug all of these things into our formula there. So A is equal to P, $750, times the bracket of 1 plus R over N, so 6% divided by 12, raised to the NT, so this is the big driver of everything, that 40 times 12 horrible, horrible mess of number, all with 1 subtracted from it, and then divided by 6% over 12, where don't do this by hand. Just don't. You've got a calculator, use your calculator for this. Your life will be better. You should get that the value of your annuity ends up being, I can't remember if this is approximate or exact, I think it's approximate, just to be sure, $1,493,618.05. Can't forget that nickel. So, after 40 years, your account will go from having $750 to $1.4 million. You'll be one of those millionaires that I mentioned at the beginning there. Hooray! Where, to be sure, if you want to find out about how much of this was interest, what you have to do is think about the fact that you're putting in $750 for 40 years, where you're putting that in once a month, so that is 480 times. So your total investment here would be $360,000, still quite a lot, but relative to that, not so much, because what you'd end up with is that your interest would in this case be that 1.4 million, 1,493,618.05 minus 360,000. I'm running out of space again. I keep doing that. These numbers are very big. Would end up being $1,133,618 and that all-important nickel. Which, if you think about that as a percent amount, the percent of the total there, that says that the interest accounts for about 76%. You can check that, you divide this thing by that thing, you'd get about 0.759. Quite a lot gets accounted for from interest, which is the main point of an annuity. Accumulating large amounts of wealth from relatively small contributions over a long period of time. And the next thing we're going to look at is the natural sort of extension that we've had a bunch of times in here, where we're going to talk about going in the other direction. That is, if you have a goal for your retirement fund or, say, a down payment, how much money would you need to be putting in there to reach it by a certain point?